SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show is also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, a new study reveals that the first stars formed later than previously thought, puzzling new questions about galactic evolution, and another close call with the Earth barely escaping being hit by an asteroid on Saturday. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New research has discovered that the first stars in the universe began shining far later than previously thought. The findings, based on new data from the European Space Agency's Planck satellite, also indicate that these first-generation stars were the only sources needed to re-ionize the universe, giving us the cosmos we see today. The study shows that the process of re-ionization was already half completed when the universe was just 700 million years old. When you think of the multitude of stars and galaxies which populate the universe today, it's hard to imagine just how different the 13.8 billion-year-old cosmos would have appeared when it was just a few seconds old. At this early phase of its existence, the quark-gluon plasma of the Big Bang had already started to condense, forming a hot, dense primordial soup of particles, mostly electrons, protons, neutrinos and photons. In such a dense environment, the universe would have appeared as an opaque fog, as photons were unable to travel very far before colliding with electrons. However, as the cosmos expanded, the universe grew cooler and more rarefied, and after about 380,000 years, it finally became transparent. By then, particle collisions were extremely sporadic, and photons could travel freely across the cosmos. Today, telescopes like Planck can observe this fossil light across the entire sky as the cosmic microwave background radiation, the faint glow of the Big Bang, just 2.7 degrees above absolute zero. Some of you may know it better as the static white noise picked up between channels on old analog TVs. The distribution of this cosmic microwave background radiation across the universe isn't completely uniform. Some areas a little bit cooler and hence denser than others. These fluctuations contain a wealth of information about the history, composition, and geometry of the universe. The release of this cosmic microwave background radiation 380,000 years after the Big Bang happened at a time when the universe cooled down enough for electrons and protons to join together to form the very first hydrogen atoms. This was also the first time in the history of the universe that matter had achieved an electrically neutral state. After a few 100 million years, as more and more hydrogen, helium, and occasionally lithium and possibly even beryllium atoms formed, they condensed to eventually give rise to the universe's first generation of stars. These population 3 stars, as they're called, are very different from the stars we see today. Because they're made only out of the pure hydrogen, helium, and lithium of the Big Bang, they were huge, massive stars, tens to hundreds of times larger than our Sun. Being so big, they only lived for relatively short periods of time. But during their brief lifetimes, they flooded the universe with ultraviolet radiation. It was this flood of radiation which subsequently split many atoms apart again, turning them back into their constituent ionized particles, electrons and protons. Scientists refer to this as the epoch of re-ionization. It didn't take long for most material in the universe to become completely ionized, and except in a very few isolated places, it's been that way ever since. Observations of very distant galaxies hosting supermassive black holes indicate that the universe had been completely re-ionized by the time it was about 900 million years old. The starting point for this process, however, is much harder to determine, and it's a subject which has been hotly debated in recent years. The cosmic microwave background radiation can tell us when the epoch of re-ionization started, and in turn, when the first stars formed. To make this measurement, scientists exploit the fact that a fraction of the cosmic microwave background is polarized, meaning part of the light vibrates in a preferred direction. It's caused by cosmic microwave background photons bouncing off electrons, something that happened very frequently in the primordial soup before the cosmic microwave background was released, and then again later after re-ionization, when light from the first stars brought free electrons back onto the cosmic stage. Astronomers use these tiny fluctuations of the cosmic microwave background polarization to determine the influence of the re-ionization process and work out when it all began, when the first stars were born out of primordial molecular clouds. The first estimate of the epoch of re-ionization came back in 2003, when NASA's Wilkinson Microwave Anisotropy Probe, or WMAP spacecraft, suggested the process may have started fairly early in cosmic history, when the universe was just a couple of 100 million years old. However, that result's a bit problematic because there's no evidence of any stars forming back then. And that would have meant postulating the existence of other exotic sources that could have caused re-ionization at the time. Luckily, those first estimates were soon corrected, as subsequent data from WMAP pushed the starting time further on into later epochs, indicating that the universe had not been significantly ionized until at least some 450 million years into its existence. This eased, but didn't completely solve the problem. You see, although the earliest of the first stars were observed to have already been present when the universe was just 300 to 400 million years old, it remained unclear whether these first stars were the main culprits for reionizing the cosmos, or whether additional, more exotic sources would still need to have played a role. In 2015, Planck provided new data to help tackle the problem, moving the reionization epoch even later into cosmic history, showing that the process was already about halfway through when the universe was around 550 million years old. These findings were based on Planck's first all-sky maps of the cosmic microwave background radiation obtained with its low-frequency instrument. Now, however, a new analysis from Planck's other detector, the high-frequency instrument, which is more sensitive to this phenomena, shows that reionization probably started even later. In fact, much later than any previous data suggests. The new data also discovered that reionization was a very quick process, starting fairly late in cosmic history and having half reionized the entire universe by the time the cosmos was 700 million years old. The new findings also confirmed that no other agents were involved, only those first-generation stars. The new study locates the formation of the first stars much later than previously thought on the cosmic timeline. In fact, it's very likely that some of the very first galaxies to have been created have already been detected with long exposures, such as the Hubble Ultra Deep Field. What all this means is that it's going to be far easier than expected to observe more with future observatories, such as the upcoming James Webb Space Telescope, which is slated for launch on an Ariane 5 rocket in 2018. A new study charting the rise and fall of galaxies over 90% of cosmic history has discovered galactic diversity in the early universe was similar to what astronomers see today. The new findings, reported in the Astrophysical Journal, raise some profound questions about galactic evolution. For example, how could galaxies which appear old and are no longer making stars have existed in such a young universe? The study's based on the Four-Star Galaxy Evolution Survey, or Z-Forge. It's resulted in the development of a multicoloured photo album of galaxies as they grow from their faint beginnings into mature and majestic giant stellar cities. The study measured the distances and brightnesses of more than 70,000 galaxies, spanning some 12.5 billion years in cosmic history, back to a time when the universe was less than 10% of its current 13.8 billion year age. The authors assembled their data by using a new set of filters that are sensitive to infrared light and taking images with them over 45 nights using the Four-Star camera on Carnegie University's 6.5-metre telescope at the La Campanas Observatory in Chile. The resulting three-dimensional map revealed young galaxies that existed over 12 billion years ago, allowing astronomers to better understand the universe's earliest days. However, discovering that galaxies in the early universe appear to be just as diverse as they are today, a time when the universe is far older and more evolved, raises some serious questions about science's understanding of galactic evolution. The fact that the team discovered young galaxies in the distant universe that have already shut down star formation is quite remarkable. Big Bang theory, backed up by baryonic acoustic oscillations, tells us that the universe back then was physically far smaller and galaxies were closer together than they are now. That would have allowed them to gravitationally cluster together more easily as they formed the nodes and filaments of the large-scale structure of the cosmic web. In fact, one of the study's first images identified one of the earliest examples of a galaxy cluster, which appears to have already been formed when the universe was only 3 billion years old. Galactic quenching caused as new galaxies fall into larger galaxy clusters, losing much of their star-forming gas in the process, may provide an answer for the early shutdown of star formation in some galaxies. The observations gathered by Z-Forge also provide astronomers with new insights into what our own galaxy, the Milky Way, was like in its youth. 10 billion years ago, galaxies like the Milky Way were much smaller, but they were forming stars 30 times faster than they are today. The Milky Way currently produces about 1 solar mass worth of stars every Earth year. One of the study's authors, Rebecca Allen from Swinburne University, says Z-Forge is providing a complete and reliable census of the evolving galactic population, allowing scientists to see how galaxies evolve with time when they form their stars and how they develop into the spectacular structures we see in the present-day universe.
So what's important about the filters that we're using is that when we sample a galaxy's light, there's many different ways to observe galaxies. And of course, the finest sampling is if you use something which is called a spectrometer, and that literally breaks up the light of the galaxy into all its constituent parts. However, to do that requires very long observation because you lose light when you break it up. And so when you use these broader filters, instead of breaking it up so fine, you're really getting larger chunks. However, the downside of that is that you're not as finely sampling the galaxy's light, so you don't really know sometimes where certain elements are coming from. Now, when you use what we call medium band filters, you're kind of playing a game where you're in between those two things. And so you can more finely sample these really important features of what we call a galaxy's energy distribution. And so this helps us understand, literally what a galaxy is made up of. Does it have more older stars, younger stars? Does it have lots of dust? Or is it, not really forming stars at all? And so this really hasn't been done out to high redshift. And that, when I say redshift, that's just a fancy word for galaxies which exist earlier in the universe. And so this helps us understand, that the galaxies that make up the early universe, they're not just these super bright star-forming galaxies, but we've got big, massive, dusty galaxies which are forming stars. We even found a galaxy which isn't forming stars anymore, which is very unexpected.
You're looking back through space-time and you're seeing these distant galaxies, and as you do that, the light coming from those galaxies is shifted more and more to the red end of the spectrum, and that lets you know how far away those galaxies are. But then you've got to take other things into account, and one of them is the reddening just caused by the dust between you guys and the galaxy that you're looking at, and also the simple fact that if a galaxy is making stars, it'll tend to have more of a bluish light, or if it stopped making stars, it'll look more reddish. So you've got all these other parameters you've got to take into account as well.
Absolutely, and that's why, having just the medium band filters, it's not enough. What's powerful about Z-Forge is we're able to utilize data from other surveys, which we call ancillary data, and then we can put all that together, and that's how we're able to really understand what kind of galaxies we're looking at. So the medium band filters are very advantageous in that it really helps us constrain an important part of the galaxy's light spectrum, which really then in combination with the other light information helps us pinpoint exactly where this galaxy is in the universe. And that's really important. Like you said, when you want to understand the evolution of galaxies, you have to know not just where they are, but when they are, so to speak.
When one looks back in space-time to the early universe, one would expect to find lots of blue galaxies actively involved in star formation, in starburst, and that's not what you were always seeing. There was one example you were talking about.
Yes, we know in the universe today we have galaxies which are big, small, forming stars and which are red and dead and no longer forming stars. But the caveat is, to be non-star forming now, you had to have been forming stars at some point. So we just expect as you go back in time, you find more and more star-forming galaxies. But what we've been able to discover with the Z-Forge survey is that already very massive, mature, dusty star-forming galaxies, and as well, galaxies which are no longer forming stars exist at these early epochs in the universe, which, we thought this kind of stuff didn't really happen until a little bit later on, or we really didn't know, to be fair, exactly, when these galaxies, early on may shut off their star star formation and turn red and dead. And so now we're able to kind of say, well, look at this. We know that they were already really massive, which means they had formed a lot of stars, and some of them have just completely passed through that star-forming phase really early in the universe, which just helps us constrain how these galaxies are assembling and evolving with time.
Was that shocking to see galaxies that have already shut down star formation so early in the universe's history?
I guess we do have predispositions about what we think should be going on. So yes, it was fairly surprising to find something that was not only dead, but also that it was very massive. And so this means that this galaxy evolved on a very short time scale, which I think that is a little bit not surprising, but it's a really interesting discovery.
Is this galaxy falling into a larger galaxy cluster? Is it losing star-forming gas through the gravitational pull of other galaxies in the cluster?
Well, I think it's certainly not far-fetched to think that this galaxy exists in a more dense region, because we do think that especially in the early universe, aids the evolution of these galaxies, and so it helps accelerate their evolution, if you will. But, it's difficult to find overdensities at these high redshifts, which, that's another accomplishment of Z-Forge, is these very accurate redshifts or locations allow us to find overdensities where before it was kind of really tricky because you needed spectroscopy. And so, at Redshift 2, which is slightly closer to the time we live in now than we found this quiescent galaxy, we found a huge overdensity. And so it could be perhaps that, like you said, this galaxy is part of some larger structure, but it would be very difficult to identify that at such high redshift.
You did find at least one example of a galaxy cluster, didn't you?
Yeah, it existed when about 9 billion years ago. So it was really forming when the universe was only about 3-4 billion years old, which is remarkable because we're really catching these filaments, which are these kind of threads of galaxies, and they have these little nodules where we can see there's probably some very large scale structure. That's, just a fancy word for cluster starting to form.
So these are the nodes and filaments of the large-scale structure of the cosmic web you're starting to glimpse at.
Absolutely. And, we think that this, what we call proto-cluster, will evolve into something like the Virgo cluster, which we see in our local universe, and it's just absolutely huge.
I guess as more and more data comes through, you're going to be able to determine whether galactic environmental quenching was causing this galaxy that looked old, the red and dead galaxy, to be the way it is.
Well, yes, it's very interesting you bring that up because that's something my research specifically addresses. And using this Redshift 2 galaxy cluster, I was trying to find evidence of whether or not environment had accelerated the growth of these galaxies and the evolution. And, essentially we're looking to see, do we have more of these quiescent or red and dead galaxies? Are there equal numbers of star forming? And it's actually very, very difficult because you have to understand that when you're looking at these images, you're really looking at a snapshot in time. So what you see could be the product of this thing existing already in an overdense region. So it's hard to constrain exactly when this galaxy quenched and how much its environment played a role, or did it just grow to be very massive very quickly and then shut off its star formation, which you would then think was linked to it just being an area which was overdense to begin with. So it's kind of circular. So we assume that there's something going on there, but whether or not we'll ever be able to determine it, we might have to wait for the next set of telescopes like JWST, where we can get imaging, really crystal clear imaging of these galaxies to look at them and try to understand what's going on with their structures as well as their stellar populations.
There's another story that came out in the past week from scientists with the European Space Agency using the Planck satellite. They've been looking back at the epoch of re-ionization, and they've found that the data they've got at least indicates that it's very likely that some of the very first galaxies have already been observed in existing telescopes like the Hubble Ultra Deep Field. James Webb will add to that by providing even further observations, but looks like we may already be at that stage where we're seeing some of the very first galaxies just with our existing Hubble Space Telescope.
Yeah, no, I think that the amazing thing about Hubble is that it just continues to produce amazing science. And I just think it's really exciting to be in this time where we are actually realizing that we are perhaps seeing some of the first galaxies. And, what's amazing is the Hubble telescope is seeing galaxies at times where we question whether they had even existed yet. So, like you said, Hubble is bringing to our attention questions that we hadn't even thought of, which then we will be able to address with James Webb, but then will probably, again, lead to more questions. So So it's this fun game of discovery and uncertainty.
When you look back 12.5 billion years and you see this light coming from so far back in space-time, how does that make you feel?
I mean, it is very inspirational in that I sit back and I think I'm actually looking back in time, that the light left these galaxies, not, even minutes or hours ago, but years, billions and billions of years ago. And so I just think it's an amazing, accomplishment of mankind that we develop these instruments and we understand what we're looking at, but that also we're fortunate enough to get to appreciate that we're just some little part of this gigantic universe and that it's all just amazing.
I must admit, I can't wait till James Webb flies and maybe, hopefully, we'll be able to actually see the light coming from some population 3 stars. That's what I'm sort of holding my breath.
That will be amazing. To really, it's great because we are kind of at the end of the story when it comes to the evolution of our universe. Yeah, and so now we're actually going to be able to really understand how it all began as well, which is great because we'll be in the time where we kind of get to come full circle, so we think.
That's Rebecca Allen from Swinburne University. It's been revealed that the Earth barely escaped being hit by an asteroid last Saturday. The 34-metre wide space rock flew past the Earth at a distance of just 84,619 kilometres, just hours after it was first discovered. The asteroid, which has been named 2016 QA2, was initially detected by astronomers at the Sonaire Observatory in Brazil. Follow-up observations by astronomers in Italy provided the orbital trajectory projections. 2016 QA2 appears to be an A10 asteroid, which is a group of NEOs or near-Earth asteroids that often cross Earth's orbital path. A10 asteroids are named after the first member of the group to be discovered, 2062 A10, which was first detected back in January 1976. Astronomers have so far identified at least 937 A10s, more than 100 of which are classified as potentially hazardous asteroids. And asteroid 2016 QA2 is no exception. In fact, it's at least twice as big as the meteor which airburst in the skies over the Russian city of Chelyabinsk back in February 2013. The Chelyabinsk asteroid injured some 1,500 people and caused millions of dollars in damage as its shockwave slammed into the city, damaging buildings and shattering glass. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show is also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, this month exploring the mystery of fast radio bursts.